Roland Snooks. It's a real pleasure to introduce, can you hear me? Yeah. It's a real pleasure to introduce Roland today because I personally find Roland to be one of the most talented and progressive architects of our time, but maybe more directly the most talented progressive architect that I know. Roland is a partner of the experimental research group Kakuja and director of the architecture practice Studio Roland Snooks. Roland's architectural design research is focused on behavioral processes of formation that draw from the logic of swarm intelligence and operate through multi-agent algorithms. In addition to his work with algorithmic design, Roland directs the Architectural Robotics Lab at RMIT, our sister on the opposite side of the world, and holds a master's in, I don't mean sister as a pejorative term, but holds a master's in advanced architectural design from Columbia, where he studied on a Fulbright scholarship after graduating from RMIT. Roland is currently a lecturer at RMIT and holds a visiting position at UPenn, but has also taught at many other institutions, Pratt, SciArc, UCLA, USC, just to name a few. And he's been published widely, including the Frac Collection in France, the Beijing Biennial, and the National Gallery in Victoria. And Roland is an extremely prolific designer and architect, and we should add researcher to that category. And what's interesting about the work is that there's a consistency that's somewhat undescribable. We had this conversation over lunch today. If you look at the student work, there's a consistency to that as well, and it's oftentimes difficult to distinguish student work from Roland work. And I have many questions about that. I'm sure we do as well here. But it means to me that there's some larger agenda that Roland's operating under that cannot possibly be about micromanagement given the complexity of the type of work that you'll see here. I think it will become very apparent, 2 minutes into this presentation, what I mean by prolific, complexity, emergence, but also the consistency of beauty that will emerge. And I hate to use the word beauty, but it only came up at lunch today, but I find the work beautiful. And I just want to quote something from Roland. The website claims that Studio Roland Snooks is a progressive architecture practice, agreed, with a passion for experimentation, questioning the norm, and developing unconventional solutions. So one of the conversations we've been having here this semester has emerged from a discussion about the plan, or lack thereof, currently, particularly in students, that somehow we're not working with plan. I disagree that students are not working through plan, but I also disagree that this conversation is interesting. I only claim that somehow, Roland, I've never seen a plan of your work, so this is a question that I have that we can think about. But I also would posit that if we mandated that architecture is the result of orthographic plan drawings, we don't get Roland, actually. And with that, I think that your work is progressing a radical vision, the future of architecture. So please help me welcome Roland Snooks.
Brandon, thank you very much for a very kind introduction. Yeah, we don't draw that many plans. They're certainly not a generator of our work. And thank you, Brandon and Nada, for inviting me out here to give the presentation today. Today I'm going to talk about the work of my two practices. So one is Kakuja. We describe it as an experimental research collaborative. It was originally established by myself, Robert Stewart Smith, who's at the AA, and Jonathan Podborsek. Now it's run by Rob and I. It started its life as a research group, and as we've become more interested in getting this work out of the computer and starting to build it, we've established separate, let's say, more traditional architectural practices not traditional in the sense of the work, but in traditional in the sense of the way that work is procured. Complex systems and their algorithmic tools have been extensively mined within architecture over the last decade. And while complex systems and their emergent phenomena increasingly define our understanding of becoming or our understanding of formation, emergence evades or sometimes contradicts notions of architectural authorship and the role of design intention. So indeed, many of the algorithms that architects use are unable to deal with design intention and unable to deal with many architectural concerns. The projects I'm going to discuss today speculate on the interwoven relationship between these two concerns, that of design intention and emergence. And in particular, this is an attempt to try and work through the relationship between subjective concerns and systemic ones, or systemic processes. When we first started out Kakuja, one of our ambitions was to try and articulate or define an architecture of swarm intelligence. We're now shifting away, I should say, we've been shifting away for several years from a purist methodological concern to one which is more about the strange or esoteric qualities that come out of the processes we've developed, and these processes are a relationship between top-down design decisions and bottom-up algorithmic techniques. Now, our work is part of a larger exploration of complexity and algorithmic design within architecture, but I would claim that the original territory that we've tried to carve out from that is to do with the way design intention is embedded within the algorithm. And in particular, the way we reconceptualize design intention as a series of behaviors and the way those behaviors interact to give rise to a sort of self-organized design intention. This is something that we describe as behavioral formation. The particular subset of complexity theory that has been most influential on our work is swarm intelligence. So swarm intelligence, as you know, is a system of collective behavior where it's the interaction of the individual elements. I'll talk about them as agents. In this case, they're birds. And the way those individual agents interact to give rise to behavior that is greater than the sum of its parts, some type of emergent behavior. Swarm intelligence is often, examples of it is often cited in biology, things like flocks of birds, schools of fish, the behavior of social insects, termites, the way termites interact with other matter to build mounds, or the self-organization of slime mold. Algorithmically, the important influence on our work has come through Craig Reynolds. Craig Reynolds is an animator, programmer, a complexity theorist, and in the early, well, I guess the mid to late 80s, he was working on something that's known as a Boyd's algorithm. The Boyd's algorithm is an attempt to try and simulate flocks of birds, schools of fish. At the time he was developing this, there was this common assumption that the way these systems worked was through either imitation or through a hierarchical system, some way in which the agents were following a lead agent. The birds were following another bird. He was able to break this down and demonstrate quite vividly there's actually a distributed system in that birds or fish were only interacting with those that are immediately adjacent to it. So he established three, I guess now classical rules, which are cohesion, separation, and alignment. So staying close to your neighbors, avoiding collision, and matching the speed and direction of those around you. And by putting these into a simple model, he was able to demonstrate very realistic flock-like behavior. Now, this is sort of an algorithmic basis for a lot of what we're doing, but in trying to bring this into architecture and develop it further, this is not an attempt to try and make architecture flock-like. It's not an attempt to try and make architecture somehow biological, but it's a different way of thinking about design intention. And as I said, it's a way of thinking about design intention as a behavior and encoding behaviors within the system. So breaking down the intention of the architect into a series of small, discrete decisions, looking at the way those decisions interact to give rise to a self-organized design intention. So if a lot of the multi-agent work that's been done in computational biology or in other fields are looking at how you encode the agency of a point, we're interested in putting agency into other geometry. So we're interested in what is the agency of a line, what's the agency of a network or a mesh, or what's the agency of a component, these things that we've begun to call bodies. This is a catalog of some of these. So in showing some of these vector-based geometric behaviors, it's a way in which our design intention is broken down into a series of, I guess, things that can be described geometrically or mathematically. 4 ways of describing a behavior. A diagram on the left explaining the relationship between an agent and its neighbors, summation of the vectors, pseudocode, and then type of code that we end up writing for one of these behaviors. And the relationship between behaviors. So the overall behavior of an agent is a summation of a series of discrete behaviors. Now, agents never operate in a way which is, or at least agents within our work, never operate in a way which is binary. It's never a certain condition or another, but it's always a tendency. It's always through the summation of these that they have a tendency to behave in particular ways, but never in absolute ways. It's never binary. Recently, looking back through the projects we've been working on with multi-agent systems for the last 12 years, we've begun to realize that there's a series of strategies that we've been deploying in these projects. And this is a diagram trying to explain the way some of those strategies begin to weave through different projects and they relate different projects in different ways. So some projects draw together and hybridize several strategies. Some are based on just one of these. The first of these strategies is fibrous assemblages. This really comes about through an understanding that matter is not homogeneous. Like matter, and particularly organic matter, is made up of, I guess, lots of very small elements, and the geometry of those elements and the relationship between those elements dictate the bias or the tendencies that material operates under, the way it behaves. So we started thinking about this as a way of thinking about architectural geometry, and started looking at fibers and the way individual fibers might interact. What are the rules for the interaction between those fibers? And then the way those fibers start to mat together to make surface or bundle to make various hierarchies. So diagrammatically, it works in a way in which an agent will draw a fiber, draw a line through space, and then those lines have agency embedded in them themselves. So those lines begin to bundle or relate to other lines. In all these algorithms work in a nonlinear way. So there's not a set hierarchy within them, but it's a mutual interaction. This draws on something that's familiar to us, which is Ferrato's work with wet grids. So on the left, we've got a series of woolen strands that are connected to nails. It's a periodic order. It's a repeating order. The middle, a certain amount of noise or randomness is added. So this is done by lengthening the strands. And then on the right-hand side, those strands become self-organized. The self-organization of that happens through, in this case, the agency of surface tension. So it's the surface tension of the water that draws these strands together. The first project we deployed this on, this is about 6 years ago now, it was a concrete shell exoskeleton tower. And we were looking at the way we could write behaviors for lines, the way those lines would start to interact, and what types of patterns and organizations that would generate. So in doing this, we began to realize that even though we weren't putting hierarchy into the system, hierarchies started to emerge from those systems. So you can see in this image, the fibers start to bundle in various places to create sort of, I guess, meta fibers, and in other areas you start to get sort of smaller cellular conditions. This is an example of what we're increasingly trying to do in our work, which is synthesize a whole series of elements to architecture which are often described discretely. Particularly, say, in classical modernism, where there's this tendency to want to describe form, surface, structure, articulation, even ornament as separate elements that could be assembled. What we're trying to do here is look at the way a single body of material, in this case it's the concrete shell of the tower, can start to negotiate between those different concerns, but we see them an architectural role as being a behavior rather than an architectural role having a one-to-one relationship with geometry. So in this case, the shell of the tower is trying to negotiate between structural necessities. It's got a series of ornamental behaviors. It's dealing with enclosure. It's swelling up at a certain place and starting to make something which is spatial as well. So something we've begun to talk about in our work is the separation of architectural role from architectural geometry. And so to say that instead of saying that that you can have a relationship between a role such as vertically supporting something and the column that supports it, we're interested in thinking about structure or any other behavior, any other role for that matter, as a behavior. One of many behaviors that interact mutually. As we're starting to look at the way some of our projects might escape the computer and be built, this is an example of looking at ways to build relatively complex concrete with relatively simple systems. So this is looking at casting concrete between, in the way that you would normally do it, between layers of plywood, but attached to those layers of plywood are a series of 3-axis milled foam. That has a certain constraint and it generates a certain type of geometry. More recently, we've started to look at other ways that we can do this, perhaps in a more efficient way. So this is an example where we have a multi-axis arm that's picking up a foam block and it's carving it with hot wire. So it's a becoming increasingly known and used technique, but it's something where we can reduce the, instead of having hours of milling time, we have a few minutes of cutting time. This makes it a much more affordable process, but what it also does is starts to change the type of geometries which are possible. So these are obviously ruled surface. It's coming from a line that's wire cutting these. And so the characteristics of the geometry change. And so we see this as an opportunity rather than a failure of the ability to achieve the digital forms that we looked at previously. So we're becoming increasingly interested in the way we might go back and forth between the digital behaviors and then, I guess, limitations or constraints of and opportunities of fabrication techniques. This is going back again further. This is a previous tower project where we started to increase the volatility of the system. So in the first tower, the strands are constrained to a given surface. So this is an interaction between the thing that we designed directly, so the surface of the tower, and then the lines which are able to have some type of bottom-up agencies, some type of emergent quality. In this, we increase the volatility, give more freedom to the agents to weave inside a known surface, and I guess make a more complex arrangement of fibers. In doing so, there's sort of many more conditions, I guess, more emergent conditions which arise. So increasingly, we're dealing with how do you enable greater volatility within the system? How do you increase the population of the system, which then affords a whole series of emergent possibilities, but at the same time bring a series of top-down direct design decisions as a way of controlling it. And I'll talk about that more as we move through these projects. Polyscale tectonics is the next strategy I wanted to get to. This is something about self-similarity, or even fractal geometry. The idea that the same operation can be repeated, or the same geometry is repeated at several scales. One of the results of working this way is it has a blurring of the role of geometry. So the role of geometry, once again, is no longer indexical, or I guess the characteristic of geometry is not indexical to its role. We've been working on several kind of strange research projects with Texas A&M from a couple of years ago. We had funding to work on projects under the guise of the House of the Future. We really use this as a way of looking at the relationship between some of the fibrous algorithmic work we're doing and our sort of emerging interest in composites. So there's two projects. They're almost like one's like an evil twin and one's not so evil. This one's the evil one. It was given the most degree of freedom. And so in this case, we don't have an underlying surface that's controlling the generative aspect of the project. So what happens here is the algorithmic process, the way the agents draw strands, is generating all scales of the building. So on one level, it's generating the overall form of the project. As you start to zoom in, it's matting together to make surface, it's bundling to make structural elements. This is sort of an experimental chunk we're looking at. Here's another one of those chunks. This is a way that we're increasingly working through small parts of the project, testing something, and then deploying it at a larger scale. So this became a sort of highly volatile project, but then we're still interested in the way we might start to make this. So this is one of our first reasonably sized composite projects, looking at the way the fibers can be built as and this one is in fiberglass. So this is the not so evil twin. This one is both these projects are obviously fairly whimsical projects, slightly tongue-in-cheek at times, but this one is trying to take a project to an extreme where structure becomes a major issue. So it's a very lightweight composite house, cantilever off the side of a cliff, and it's sort of tethered back with these tentacles which get cut into the cliff, into the cracks of the cliff. So in this project, the relationship between surface and line became very important. So in the previous project, we allowed the lines to generate the form of the project. Here, we're constantly going back between surface and line, and so which is surface being a top-down series of decisions, things we directly model, and the lines which are coming out of this emergent process. And it was decided that this version of the house would be something which is highly controlled by the surface. So you can see in the end it becomes a much cleaner, but maybe also a lot of the form of this project is something which it's sort of less strange, I'd say. It's more known. Once again, it has a polyscalar set of fibers. And we're interested in the way that this layering of fibers starts to give a reading of depth in the skin, and the way at night this has a very different reading. Starts to silhouette those. Once again, we're looking at a chunk of this, how one small part of this might be fabricated, and part of this was to try and really work out whether this is, these things are entirely whimsical or whether they have some bearing on reality in terms of fabrication. I'll come back and talk more about the prototypes later on. We were working with the aerospace engineering department at Texas A&M, and they were convinced that the building was more likely to take off due to the uplift from the heated cliff than to fall down. The final image of that. So those projects were done a couple of years ago at Texas A&M. This is going back again. This is 2008, and it's a competition that we worked on in Taipei. It's for the Taipei Performing Arts Center. This is probably the first project where we started to seriously consider the relationship between top-down and bottom-up. So I guess when we were first starting out Kakuja, we were obsessed with algorithmic work. We were interested in the possibility of making an architecture purely from bottom-up emergent systems. As we started to tackle more complex projects, more complex briefs, we of course began to realize that this is never going to be able to produce a complete architecture, and architecture is always going to be the interaction between, or at least our architecture is always going to be an interaction between subjective top-down decisions and those which are more systemic. The project has three parts: a fractally subdivided podium, 3 auditoriums, and a sort of all-encompassing roof. This is a project we're looking at a different type of algorithm, a recursive algorithm. This is dealing with fractal subdivision. So this is a way of generating detail, I guess, and texture. It was used in both 2D and 3D. So in 3D, it's used to subdivide the base. This was to try and get the scale down to a human scale, also related to the scales of the adjacent buildings. And then it was used on the interior, partly as a way of subdividing the surface for acoustic reasons. It's not there's not an ambition to make this acoustically optimized, but to, I guess, make it acoustically effective. But more so than that, it's really an attempt to try and bring a certain level of ornamentation back into auditoria, which increasingly become, I guess, bland. For those of you who know Melbourne, this also sort of owes a certain debt to Story Hall by Ashton Raggett McDougall. Anyway, but it partly comes from nostalgia, like our nostalgia for the concert halls and operas of the 18th and 19th century. In the other hall, this is a three-dimensional subdivision in timber, the multi-purpose hall in the Opera House. But what I really wanted to talk about in terms of this project is the roof. The roof was originally modeled explicitly, directly, as a network of lines and nodes. So a surface, effectively. So the relationship between the bottom up and the top down became modeling the roof as a top down surface and then encoding agency into all of the nodes, allowing those nodes to break their links and reform links. And this meant that certain parts of the roof would begin to reform and certain parts would be left, I guess, more rigid in a way. So you can start to see where this begins to split apart. A lot of the early studies for this was looking at the relationship between blurring of geometries, so blurring of line and surface, and trying to get a fairly seamless relationship between the two. This probably wasn't successful in this project. I think what's happening in this project is it's really defined as a surface, which then has a space frame beneath it. So these things are sort of breaking apart and becoming separate elements rather than a sort of blurring or transition between the two. But it's something we keep revisiting in future projects. So a lot of the work, all the work I'm showing today is coming about through multi-agent algorithms, and certainly that's one of the dominant strands of research in our work. It's an algorithm that deals with local relationships, never with the totality of a system. So this generates a set of problems which can be described as coming about through global ignorance. So global ignorance is a necessity for emergence. It's only because the agents have a local understanding of what's happening locally that they generate complex order. However, there are some systems or some concerns or some architectural problems which can't be solved locally, and you need to have an understanding of the totality of the system in order to deal with it. And these are all topological. Things like enclosure or spatial topology or structure. You can't analyze discretely a small part of the structure without understanding the flow of load through the entire structure. So these are issues of topology, of connectivity, and they're issues that have to be dealt with globally. So in working through these systems, we've made a series of problems for ourselves, and we've spent the next few years trying to unravel those problems or solve those problems in different ways. One of the ways we solve it, or try and deal with it, is through this next strategy, which is strange feedback. Strange feedback is about a sort of messy relationship between bottom-up and top-down. So in the previous project, the Taipei Performing Arts Center, there was a sequential relationship between the two. So the top-down direct explicit modeling happened first, and then parts of that were allowed to reform. Whereas in strange feedback, it's not clean in that way. It's not sequential. There's a constant looping back where we would model something, put that in as an input to the algorithm. The output of the algorithm becomes the input to modeling, etc., etc. In a way that the starting condition, or which comes first, whether it's the modeling or the algorithm, becomes less important. This is the project where we really started to develop this strategy. It's a project in collaboration with Tom Wiscombe, and it's a competition entry for an expo in Korea for the 2012 expo. It's a thematic pavilion. The theme was about water and the ocean and people's relationship to the ocean. But anyway, it sort of becomes this, I guess when Tom and I first started talking about it, we started talking about it as some sort of strange sea creature or monster. And anyway, it's a series of objects, and it's a series of objects that are connected by a membrane. So that we have a series of like these kind of avocado-looking things, and then objects within objects. And this is something that Tom Wiscombe is continuing to pursue, this idea of, and it's one of the first projects in which he started talking about it, the way an object sits within another object. You can see that in the section here as well, or the way that object starts to impinge on the space of another. But what's perhaps most relevant to the argument I'm trying to make today is the polyscalar nature of the project. You can see in this image that there is a blurred relationship between, I mean, it's the same geometric operation happening in a series of scales in terms of these sort of branching veins. At one scale, they're operating spatially, and they're starting to organize the space. Another scale, they're operating formally. They're also operating structurally. They get down to a level of from major structure down to stiffening of the membrane. But of course, they're also ornamental. So in this image, you can see a sort of blurring of that, where the reading of at what level it's working becomes less clear. The algorithm developed for the project was it's a type of strand branching algorithm. This is perhaps the most pure output of the algorithm that made it into the final project. This is the veins that run across the main windows. And so it's a line that's getting drawn. Those lines are branching. As those lines come close to other lines, they begin to bundle. But we're constantly working back and forth between things that come out of the algorithm, patterns, networks of lines, and things that we model. So we would typically work from something like this. We'd model something like that. We'd go back. We'd rewrite the algorithm. We'd rerun the algorithm. We'd use the geometry that we've modeled as an input back into it, et cetera, continuously going through this process. Sometimes this would make sort of strange Frankenstein things. Other times we would, I guess we worked through that until there became a certain synthesis between form and articulation in the project. And this was partly Tom and I also coming from very different standpoints in the way we design, even though we have a lot of shared sympathies in terms of, I guess, formal sympathies, in trying to bring a kind of way of working in correspondence, make some sort of synthetic relationship between the way we each work. Color became a fairly important part of this project, but it's not an indexical one. So you can see here that the veins start to get brighter and get more yellow as they get towards the tips, but it's not entirely consistent. So it has a tendency to do something, but it's not. This is done in a sort of, once again, a messy, strange feedback kind of way. So it's not something which is entirely uniform. So throughout this whole project, we were making something which was coherent, but through an inconsistent process. We worked with a brilliant young engineer, Matt Melnick, on the project, who was at Bureau Happold at the time. And so it's a series of beams that sit within this composite shell. There's two types of inflation happening in the project. So there's sort of the space inside, the avocados are inflated, much the same way that many sports stadiums are, like with a low pressure. And then there's high pressure veins that run through the membrane, and that gives it an extra stiffness. So the blue is entirely stiff. It's a fiber composite, and this is an ETFE membrane. So once again, working through a series of chunks, and then we'd often develop something at the scale of a chunk in terms of what's happening with the glazing, the skin, the interior, and then try and develop the project out from that. One of the things we began to realize when you section through some of these is the bundling of these fibers begin to become almost Gothic. And that is, I mean, you can talk about the Gothic as being something which is polyscalar. It has a self-similarity to it. Photograph of a model. Brings me to the next project. This is a project, it's competition was shortlisted on for the National Art Museum of China. The brief for the competition was for the largest museum in the world, largest art museum in the world. It's going to be located in the Beijing Olympic site, so just north of the Bird's Nest Stadium. It's an interesting and difficult site because you have a series of monumental objects, the Bird's Nest Stadium, the water cube, and so the question becomes, do you try and make another object which competes with those objects? Do you try and bury the project, but it's too big to bury? So how do you deal with this? And the way we started to think about it was, through some notion of a formless form, could we make a form that's more diffuse? And we started looking at clouds. We were working with a Chinese architect on this project, Ju Pei, and Beijing-based architect. And he was also interested in this idea that clouds hold an important role in Chinese culture and Chinese art. So we started dealing with this, and one of the, I guess, results of that is the algorithm that we developed for the project is less of a self-organizing algorithm. It's not an algorithm that's attempting to solve a particular problem or negotiate between a series of concerns in terms of structure and ornament, for example, which a lot of our projects deal with. Instead, it was an algorithm which was closer to, it was an agent-based algorithm that was closer to a fluid dynamics algorithm. So it starts to simulate turbulences and flow. We think this is perhaps one of the more successful images of our work in terms of the relationship between articulation and form. So I think the worst projects that we create are where we have a surface model of the overall form and the articulation is something which is overly applied to that form. Whereas in this image, I think it has a fairly good relationship in terms of the articulation, so the scales, the structure, the form, in a way that even though this is a very sort of thin surface, it has the sense of volume. And I think it's partly because of the relationship between those things. Now, of course, when you make this kind of massive object, you can't make it diffuse. It's still a massive defined object. But anyway, I guess we started using the cloud analogy more as a generator than a metaphor. We were working back and forth between these two ways of working, between the surface model and the agent model, until they came into correspondence. That's some idea of how massive the building is. It's a series of concrete beams that are connected by floor plates internally. So these concrete beams contain what is relatively conventional gallery spaces. And then the cloud, the structure of the cloud delaminates from the skin and starts to attach onto those. So this produces some quite, let's say, normative gallery spaces, these top-lit spaces, and then spaces in between which become less formal exhibition spaces. And we're interested in the correspondence between form, structure, and articulation. And this is something that's I've obviously talked about and is recurring in our work. So that's the substructure for the framing for the glazing, some notion of what that might be at least. This is another one of those chunks. I guess we often work this way to try and figure out what is the relationship between the parts. This is a model of that, looking at the way all these glass shingles are identical shingles, but they overlap in a way that gives them the freedom to create a greater complexity of form and distribution as well. That's one of the studies from that. And that, I guess, looking at the model, it gives you some sense of the relationship between the flow of the shingles and then the flow of the form. Quickly to the interior, some of those floor plates are connected. The beams then begin to enfold to make vertical circulation. And this is a study for the ground plane, for the paving. So the same algorithm that was used to form the cloud is used to carve out the landscape. And so you can begin to see the flow of that. But as you zoom in on this, this is an example of, it's a sort of corrupted Voronoi algorithm. Now, a Voronoi algorithm, which I'm sure you're aware of, has a very recognizable character. So it's one of these algorithms which has an indexical or causal relationship between its process and the image of the thing that's created. Now, this means that often within algorithmic design, design is actually reduced to selection, as opposed to selection and possibly evaluation, as opposed to sort of a form of invention. And this is something we're always kind of critical of and wary of. And so whenever we look at an algorithm, we're always trying to work out how can, well, one, can we embed intention into it, but also how can it be rewritten in such a way that has a set of unique characteristics that it generates. So this is a Voronoi algorithm that's been subverted in some way to create something which has a slightly, I guess, more unique or a stranger characteristic to it. Usually the competitions we do, the competitions we lose, which is to date all of them, seem to go nowhere. But the competition we did with Tom for the strange sea monster, that was for the 2012 Expo, which is in Korea. The organisers of the 2017 Expo saw that and assumed that because we've lost a competition for a pavilion, we knew what we're doing with the pavilions, and they invited us on the shortlist for the 2017 Expo in Astana. This is a much larger project, so it's for the whole Expo site, and it was working with somebody else's master plan to a certain degree. The theme of this Expo is about energy. Kazakhstan is a oil-rich and natural gas-rich country, or becoming a very wealthy country because of those natural resources, but they're also aware that those natural resources are finite and will run out. And so they were interested in theming the Expo around the new energy paradigm. And so from this, we looked at a form of sustainable energy in terms of wind. And so we're trying to use wind as a way of generating electricity, but we wanted to visualize wind, and we wanted to use it as an architectural generator, in some way make our buildings respond to it in a performative way. So what is the relationship between those four things, and how do they sort of negotiate to make architecture? So there's the 7 pavilions. I'm not going to show those. Then there's a series of, I guess, networked exhibition buildings, which look a bit like this. But what I really want to talk about is the main part, or I guess the feature part of this project, which is the symbol. Now, expos always have this kind of symbol, this big object that they build. Paris had the Eiffel Tower. Kazakhstan could have had this, but they're not going to. And what it is well, all the hairs on it are generating electricity using a piezoelectric technique where when a material compresses, it generates electrical current. And so as these hairs wave in the wind, they create electricity. So this is a known kind of used technique, normally used on a larger scale. The thing generates electricity. You also visualize electricity in the way that, or visualize energy, wind energy, in the way that these things start to swirl and start to move around. The form is generated through an algorithm that, similarly to the glass cloud, is dealing with the flow of fluids, the flow of fluids and gases. So it's sort of its turbulent type form. Now, I guess that's one way of, and we want to try and make a relationship between those things. So the way that the form is generated from the simulation of wind. As wind flows around that, that generates certain patterns. Those patterns are visualized through the movement of the hairs. The other way of talking about this project is to say that when my business partner Rob went over to Kazakhstan to meet the head of the jury, who's the president of the country, he realized a few things. One is that Astana, the capital of Kazakhstan, is full of massive gold monumental objects, normally kind of big platonic shapes. But the president also is really into horses and eagles. And so this is a golden eagle horse. Anyway, we couldn't convince him. That's it on closer inspection. So it looks a bit like an eagle. And a few plans, just for Brandon. We'll go over them very quickly. Which brings me to the next strategy, which is agent bodies. Okay, so I've talked about the way you encode agency into a line, the way you encode agency into a point. In the Type A Performing Arts Center, we were encoding agency into a network. So looking at the topology of connectivity. This is an idea that you could encode agency into a component, but not a component being a single agent, but a component being made up of, I guess, lots of small agents. So this comes about from looking at these types of images, this idea that an agent can use its body as a form of geometry, or architectural or structural geometry, connect to those around it. The first project we worked on with this strategy this is a study for a ceiling. So it was a competition. Again, this was for a museum in Poland. And this started out as a field of bodies. And as those bodies started to interact with each other, you can see an emergent figure that comes out of this field. So I think this is one of the better images in our work to sort of understand the relationship between local interactions, which leads to the emergence of, or the self-organization of a figure that emerges at the macro scale. As you start to zoom in, you see a whole lot of different conditions. So you get these sort of singular, sort of wing-like conditions. There are a series of, I guess, repeating or periodic, near-periodic conditions. As you go in, you see these types of images which are near symmetries. So not exact symmetries, and they're not symmetries which have come about from the code or from the component, but they're symmetries which come about by a certain type of interaction between the coincidence of a certain type of interaction between two sets of agents, two sets of bodies. Now, as you begin to zoom in, these things, I guess you see more of their specific qualities. And this project was done in 2009. When we did this project, I guess it was at a time in computational architecture where there was a lot of parametric architecture that was dealing with smooth gradients, or a lot of architecture which was focused on the surface. And in making something like this, it had a quality to it which was a little bit, for us, unknown. Like we started talking about it as being strange. So this goes back to the question that Brandon raised about beauty. Strangeness is not something which is beautiful, and it's not something which is ugly, but something which is somehow unknown or less known. And this has become something which we use as a way of a criteria for our work in the office. So we were always asking the question, is something sufficiently strange? Does it have a quality which is, we hesitate to decide whether or not that is it's somehow successful. So it's the hesitation about knowing whether it's successful for us makes it somehow successful. So anyway, I should say that strangeness has a habit of being normalized. So I think when we created this, at least for us, it was a strange thing. I think this is now something which is, those characteristics are more widely spread. The agent bodies found their way into this project, which is a memorial and museum in Kiev. It's a Holocaust memorial at Baba Yar. Simple diagram explains what it is. It's a monument as a space, not as an object. One part of the multi-agent generative system used in the project is in the landscape. So we've taken a charged field, so we're not assuming the landscape is neutral, and then we're releasing a series of agents into that field and looking at the way they navigate it, and what type of figures or patterns emerge from that. Now, I'm showing this is, I think, the only time I show several iterations of something, and I guess it's a way of indicating or talking about the fact that when we're working algorithmically, it's not a situation where we write an algorithm, it produces something, and we accept that as the output. It's obviously something where we're producing many, many iterations, but not a catalog of iterations from which we choose from, but we produce iterations, we go back and we rewrite the algorithm, we change the parameters, we produce new results, and we are constantly doing this. And this cites evaluation as one form of design intention. So I started off the presentation talking about the way you can embed design intention within a multi-agent system. And I guess that's originally was the primary source of design intention within our design process. But then, of course, as the algorithm produces something, you evaluate that. That's another form of design intention, and then you feed those back in. Now, in this case, we're just evaluating it in terms of its quality as a pattern and a way we think that pattern might potentially be useful in terms of a landscape, a figure of a landscape. I'll talk about the way that relationship between encoded intention and intention as evaluation changes in some of the other projects. So that produces this landscape. As you move through the landscape and approach this, the building, it's a sort of monolithic rock. And while most of the projects I've explained so far, I've talked about making a synthetic relationship between things, like a synthetic relationship between structure and ornament, or articulation and form. This is doing the opposite. This is very deliberately setting up contrasts or juxtapositions as a way of creating tension within the project. So it's a monolithic stone, but it's trying to cantilever. It's sort of trying to fly at one edge. As you move towards it, it's a relatively smooth concrete, and then the memorial space inside is this highly intricate bronze interior. So it's the bronze interior which is using the agent body technique, and this is something where each of those components are beginning to attach to each other and interact in various ways. And that's carving out the space, but then also making this very thick surface. Now, this is very deliberately trying to make a space which has a certain intensity to it. It's making a space which is supposed to provoke a visceral response to it. It's not deliberately referential in any way. I mean, people have talked to me about this and say they can read in sort of flames or melting bodies or something. We're not trying to make a sort of anything referential, but we are trying to create a certain intensity. So, some diagrams of the way those multi-agent bodies have worked. So the body itself is very simple, but it's interacting across at a series of scales. So I guess you can describe this as a polyscalar project, even though that's not really expressed within the geometry. The other contrast exists between this this intense memorial space and then the much calmer gallery spaces. So these are meant to be much more contemplative, but inside, in the middle, there is this faceted concrete wall which alludes to what's behind it. So it always has sort of this presence, but is never directly articulated. And that's a model of the project. So the geological forms from that project found its way into this project. This is a project that we've been working on for a couple of years out in California, in Malibu. So it's on a relatively steep slope. It's overlooking the Pacific Ocean. Now, the geological forms, in this case, are brought into the project as a way of trying to resist known architectural articulations. So it's an attempt to try and make it look less building-like, I guess, in some ways. The site is... Site's an interesting site. Apparently in Malibu it's very hard to get planning permission, planning approval. And so our client bought a block of land which already had planning approval on it. It had planning approval for a Spanish mission-style mansion. And apparently in California, if you you've changed the design and you build entirely within the envelope of the existing building, it is a minor design change that doesn't need to go back for planning approval. So this is a minor design change to a Spanish mission-style mansion. So the project, it's a little bit hard to see, but there's a sort of this green line here is the line of the original the planning approval, and we had to basically contort and squeeze and carve and facet this object until we could get it to fit inside there, and then produce a series of formal qualities or expressions that we were interested in There is one part of it which is less, it's done in a less direct way and has more negotiation between algorithmic processes and direct formal ones. This is a surface that negotiates between its part ceiling, its part column. It's got a chimney that comes down. It's got it comes down to support a stair at a certain point. And then the pattern on this is driven partly by structural heuristics of the agent and partly by ornamental effects that we're interested in. So you can see that the algorithm relates strongly to the algorithm from the tower projects. It's about the bundling of lines, of fibers. But in this case, we're treating them graphically in a different way. We're starting to increasingly make more models as a way of testing these things. We have some relatively good workshop equipment at RMIT. And then also use that equipment to start to prototype parts of the building. Now this is the pattern for a wall, a timber wall that we're developing. This is an example of a multi-agent algorithm which is used not to self-organize or resolve a particular problem or have particular design intention built into it, but simply as a way of generating patterns that we're interested in. So it's a sort of a highly aesthetic use of the algorithm, which we're milling out to make those types of effects. Okay, manifold swarms. This is the next strategy. This is an attempt to try and get around this problem of global ignorance. So if our algorithms can't deal with topology, then they can't deal with some fundamental architectural problems like spatial topology and closure. So in this case, what we tried to do is write a series of rules for the algorithm in which the agents could look at the agents around them and try and make clean manifold surfaces from interacting with them. So has these types of rules. Here's one of the first tests from this. So we start off with two planes, we disturb that, and then they reform into making a clean manifold topology. Now, I guess one of the things about this is, in terms of design intention, our design intention is encoded into the agent itself, but the intent is about the thing that it's going to generate. So we write rules in an attempt to try and make something which is at the level at which the swarm emerges. So we're writing rules with intention for the macro scale. This is the first project we use that on. This is New Taipei Museum competition entry. This is from another project we used it on. So this is looking at the idea that an agent that's used to develop the spatial topology of a project might also be used to develop the tectonics for the project. So each of those agents that are making the space are given a body. Those components begin to interact with lines around it and make the topology. So in this case, you can see that design intention operates at a series of scales. So on the one hand, design intention encoded at the local scale is dealing with a larger scale, like we're trying to make something which has a clean topology. And then with the bodies, it's not about the emergence of the overall system, it's simply about the local relationship. So a local behavior is written for a local relationship as opposed to local behavior for a global relationship. Anyway, it produces things like this. But that local rule I was talking about is about making the continuity of this type of woven surface. In that project, we have some studies about the relationship between shifting from surface and the way surface begins to unravel to make network. What type of geometries that might take on. And also looking at the way these become a type of almost like a fabric, and they shift between different conditions. And in this case, we've got conditions which are knitted as opposed to woven, and the way that those conditions are a change in kind, not simply a change in degree, but they happen within a continuous system. So it's not something which has a catastrophic change, but it never becomes a collage, or never becomes the meeting of two systems. It's one system's able to express those things differently. This is partly a reaction to what I was discussing earlier in terms of the sort of the proliferation of smooth gradients within parametric design. This tactic was first used on a project in Helsinki, Aalto Architecture School, Aalto University. It's a roof plan of the project. So it was used for the design of a skylight that was meant to be built from composite material. And it was redeployed again in this project. This is a project in Melbourne. It's the Flinders Street Station competition. It's a slightly difficult site. It's a railway station that cuts off the city from the river. And the aim of the competition was to try and connect those two. And so it's a surface which tries to connect to Flinders Street here. Swanson Street tries to go from the height of the bridge down to the level of the bank, connects up to the old station building, vaults over the railway, has a series of towers which are an injection of these small bits of program on the site. So it's a plaza as well as a roof. This was really, it was a surface that was modelled in a similar way to the Taipei Performing Arts Centre, the green roof. So it's a surface which is highly modelled, and then parts of that, as you get into the detail of it, begins to unravel and is generated through this manifold swarm and agent body technique. So it starts to produce these sort of delaminating surfaces, which then become quite topologically complex. Okay, so that's something we became quite interested in, and then we started to ask questions about whether there was a way of building that, and this brings me to the final strategy, which is we call behavioral composites. Now, so part of this is a material strategy. It's like, how do we build these types of forms? Part of it is trying to push the algorithmic logic to its extreme. So in the case of fibrous assemblages, where we're encoding behavior into a line, I guess the question is, what scale is that line, or what's the smallest scale could that line be? Particularly since we're making the argument that if we increase the resolution or the population of these systems, then we have a greater opportunity for complex order and emergent affects. So then I guess the argument is, can we go down to the level of the individual fiber within a composite fiber and write the behavior for this and its interaction with other fibers? So this is something we've been working through with several experiments, several prototypes. These ones were done in the collaboration with Texas A&M. This is from Tonji University. Another one of those prototypes, two of those prototypes from Texas, a recent one from RMIT University, and one we did with students in Helsinki. So this is perhaps the most ornamental of those. And this brings me to the last project. So this is a project we worked on for an installation last year, and it's really trying to test the strategy or the geometry that was designed for the train station, and see if we could build something which is similar to that at a small scale. So this is it's 2.5 meters, so it's about 8 feet tall, but it has a very thin surface. The surface is less than a millimeter, so it's 0.85 of a mil. It's fiberglass. That fiberglass is very weak. It's very flexible at that scale. And then the agent bodies, the black bodies that you see in here, these are made from expanded polyurethane foam. So they're very weak as well. They're kind of highly flexible and they're floppy. But when you put these two very flexible things together, they make something that's very rigid. So it's a form of composite. And it does that by the type of geometry that the component imparts on the surface. Basically, it makes a series of continuous ridges that run through it, corrugations. Obviously, part of the strength of the piece comes from its overall geometry as well. There's a lot of double curvature in it. This is a manifold swarm project, so we start off with a cloud. This cloud starts to reform. Certain parts of it we clamp, because we want this thing to have kind of wings and feet, and then we allow other parts to reform more, such as in the middle. So it becomes the most, I guess, topologically complex part. This is a diagram of one of the bodies. It's basically made up of a series of lines where all the control points of the lines have agency encoded into them. They're designed so they can't stretch, but they can bend. That's what the material does. It has very little stretch, but it's very flexible. I want to talk a little bit about the process of making it. We, both 3 and multi-axis, milled out formwork for it, so just out of EPS foam. That became a complex jigsaw puzzle that we put together. It gets covered with a number of layers of epoxy. You can see here the pattern of the agents is milled, sort of embossed into the surface. And the way that's made is several layers of glass fiber fabric are laid onto the mold. The bodies are placed in correspondence to the milled negatives of those. More glass fiber is added to the top. Then there's several layers of things like release film, infusion mesh, vacuum bags, and it's a process called vacuum infusion. So it's where you put it under vacuum, you draw in resin from one pipe and you sort of pull it out the other pipes, or at least pull the air out the other pipes. This is what it looks like when it's in that process. And then you tear off the release film and you're left with this, I guess, highly compressed composite. That's it when it's still in the mold. That's us ripping the formwork off. We're a little bit nervous about whether it would stand because it is extremely thin. So we left some formwork on while we were testing it. It does just stand up. This is probably the image that really explains what's happening. You can see here with the fabric going over the agent body, that body and the way that body is linked to other bodies makes this continuous network of ridges. And so it's those ridges which give it its strength. So I think the reason for ending on this project is because it embodies some of the concerns for synthetically relating different parts of architecture. So this is something where its structure is a product of its form and of its pattern. The same algorithm which is generating its topology is also generating its articulation, its structure, and obviously these bodies are also ornamental. So it's something where the whole is irreducible, something can't be removed without literally collapsing. And so it's a way of making these things, I guess, having a sort of synthetic relationship between them. So while our work, just to conclude, while our work is deeply engaged with emergent processes, these are not something that we rely on for the value in the work. So when I present the work, yes, I talk about the emergent processes that we use and the algorithmic techniques, and certainly when I talk to students, I discuss it in these terms. But ultimately, we want these projects to stand for themselves rather than rely on the value of process. But at the same time, it's saying that it's not an attempt to devalue process because it's the process, this negotiation of algorithmic and computational systems with highly subjective intention, which is, it is that process from which the strange and intricate characteristics that we value in the work come from. So we're always trying to balance between these two, between the obsession with the object itself, our obsession with process, and the relationship between the subjective and the systemic. Thanks. Do we have time for questions?
So I have, well, first of all, thank you for the, obviously, as Brandon mentioned, prolific and exuberant work that you've shown us here today. So I actually have a ton of questions afterwards, which is probably a good sign, but I'm going to cheat a little bit. I'm only going to ask one, but I'm going to cheat by mentioning others that I wish or hope someone else will ask. So, I mean, I think that there are some obvious questions that are emerging here. So one of which is the question of scale and its relationship to motif, which actually tends to undermine logics in certain cases for the sake of the appearance of those logics, right? Which is a question around this polyscale idea. Another question that I might ask is a question of critique and judgment at this moment of sort of digital exuberance and the sort of the proliferation of all of these techniques and all of the forms which, as Brandon said, were rather indescribable, how you actually then characterize, qualify, and choose among the things which are produced as part of your process. So those are the two I'm going to cheat on and not actually ask, though I think they're important. And then the one that I'm actually going to ask is actually a little bit more about intent. So you describe this relationship between the kind of the top down and the bottom up. At some moment you describe that actually as the subjective versus the emergent, as the designer intent versus the systemic. These are the kinds of characterizations that you gave us for this, this binary between these things. And I want to phrase it just actually as a kind of question about all of the other kinds of pressures that exist in architecture, all of the other kinds of contingencies, all of the other kinds of mandates, and whether you think your work and the algorithmic and systemic provocations that you're up to will eventually be able to account for all of those contingencies, those things which sit actually between and outside of either one of those specific intents. So right now your work, when you need a floor plate, you actually surround, you know, a simple plate with the exuberant form that you're super interested in. When you talk about structure, you talk about structure as a kind of rationalization that allows the basic overall form to still emerge, as opposed to the contingency of structure which might actually press into entirely new forms, right, these objects. The contingencies, let's say, of fabrication and construction processes and how they are scaled, they are not polyscalar, right, like that you have to produce things at a certain scale and certain methodologies. And so that is my question. Do you think that this algorithm, you intend to take on all of these contingencies eventually, or do you think there will always be other third terms?
Well, I guess the first way to answer that is that we're not trying to make something which is entirely systemic. I mean, which is obvious from my presentation. And so we don't need to try and build in all the things that you talk about. However, a lot of those things we are starting to try and deal with. So the first one you talked about in terms of, okay, it's made this form, now we'll throw some floor plates into it. I mean, the manifold swarm work that we've developed in the last couple of years is an attempt to overcome that. So it's how can, you know, spatial topology be emergent. I think a lot of the other, let's call them more pragmatic issues of architecture, I see as not things which we want to allow to generate the architecture, but to condition the generation of the architecture. So for example, structure. We've done some work in the last couple of years with Bureau Happold where we look at building structural heuristics in its behaviors for the agents. So the agent is it's being used to generate some sort of form or organization or tectonic. That's jumping out, being analyzed, and then the analysis is being brought back in, and each of those agents is responding to its deflection and stress by making, through behaviors which are heuristics. So, you know, perhaps if the deflection is too great, they're trying to have vertical separation to create greater structural depth, these types of things. So it's a way that it's not post-rationalizing the structure, it's not producing something and saying, okay, we need to then optimize the structure, adjust this thing. And it's not making structure the driver, but it's simply the structure becomes one of the behaviors that conditions what the agents do. Increasingly, we're starting to do that with material as well. We're looking at the way materials bend and twist and building that into some of the strand geometries and saying, okay, can we encode material behavior? Often as a limit, though, more than something which is active. So the projects are still being driven by our more esoteric design concerns, but they're being conditioned by those. So yeah, certainly we are trying to build some of those things in increasingly, but also I don't feel as though we have to build all those things in because we're constantly going back and forth between things that are direct and things which are generated. So that answers part of one of your questions, maybe.
I know Austin has a question, but while you're doing that, do you think you could go back to the slide where you had the project come down as a chimney?
Mm-hmm.
You can do it without the microphone. Okay, thanks for sharing really beautiful work. I was interested in the project in Kiev where you're showing the landscape. and you, in the process of designing the landscape, you showed a moment where you described it as a charged field that the agents were working within. And I thought it was interesting. That was one of the moments where you sort of described the spaces within which the multi-agent swarms of the agent simulations are happening. And I'm wondering sort of what the role is in your design process of not only designing the sort of rules of the exploration of those spaces by the agents, but designing the spaces themselves so they have a bias to them, or is that integrated into your design work?
Well, I mean, that's certainly happening in terms of this strange feedback process where we're modeling things. What we're often doing is modeling geometries and putting those in, and the agents are responding to them in terms of attraction. Basically, it's like they want to flow across them, or they want to, be near those surfaces in some way. So we're always designing charged spaces, I guess, in some way. Except mostly we're doing it through explicit geometry that's going in. Whereas in the case that you talked about, the Kiev Memorial, that landscape is something which is a gradient of influence as opposed to influence of a surface.
There are moments in your work where, everything is being attempted to be integrated. This is an extension of Joel's question, basically. And then there are others where the disjunction between, let's say, envelope and program becomes more apparent. In the National Museum in China, the one drawing that you show that makes that explicit is where there's a building essentially cloaked in, a swarm of bushy and hairy stuff, right? And I'm interpreting that as a very explicit and unapologetic relationship. Is that correct? And I guess the only thing I take issue with is not the project that you're after, but the fact that you call the other stuff pragmatics. Because maybe the issue is not about pragmatics, because the problem with the discourse on pragmatics is that it presumes it's solving problems, or it's addressing things like water leakage and those things that need accommodation in architecture, like where the closet goes or where the services go. And if I could slightly retune the question to suggest that maybe I'm putting words in Joel's mouth, but maybe it has maybe that the architectural enterprise has something to do with the negotiation of various concurrent systems. And there are many approaches to that, one of which is the attempt for integration, and the other one is establishing a loose fit where complexity and contradiction are enabled and are part of the expression of its outcome, while not solving any problems, because we're not interested in solving problems in schools of architecture. We acknowledge that there are multiple discourses in conflict with each other and different modalities of putting them together. So I guess I'd ask you to go one more round into Joel's question about what the next step is in this work. To what degree do you begin to take on all of the various systems under the banner of your research, or will you be satisfied in 5 years to find a box surrounded in your research? I'm also reminded here of just an anecdote to end with that I don't remember now who. It could have been Alejandro or Farshid, or it could have been a critic that was speaking about their Yokohama and basically announcing the death of the plan, because there's no plan of that project that really describes it. But at the same time, once you get into the sections and the multiple sort of CAD scans, you sort of understand, oh, this is really about multiple sections, and the project becomes very clear at that point. There may be an entry into your project by way of the dealing with scales, such that you're dealing with the scale of the fiber at the nanoscale, you're dealing with the scale of the overall figure, which clearly you have illustrated well today. But that intermediary scale does not seem to be there. Or when it's there, it's almost teleological, because it goes back into its own systems as a way of demonstrating itself. Do you have, do you develop algorithms that absorb the stubborn ready-mades of the world as part of your system and envelop them? Maybe it's a Lowesian argument to some degree, but I wonder what happens when you and Lows come together. Sorry, it's a little bit too long, but
inherently, the whole logic of what we're doing is about negotiation. So its ability to kind of absorb something else, some ready-made, in theory, it should be able to absorb it relatively well. So in theory, it's a type of strategy that can, reorganize or respond to, different like things that are thrown in at it, different constraints. But in terms of, you're asking where the work might go next, I think there's an ideology or overly ideological ambition in the work to make it synthetic, synthesis of all these things. And I think that, yeah, in my work. But I think that's something that's starting to dissipate. Like, I think I'm becoming less interested in the totalizing. It's never an aim to make a totalizing system, that's for sure. But there certainly has been an ambition of trying to make this way of designing through multi-agent systems able to operate at all scales and with all, let's call them for now, architectural problems, architectural concerns. I think where the work will change and where it'll start to become more interesting is when it starts to get built. Because as soon as it gets built, it's going to have to deal with a whole lot of other issues. And they're not the pragmatic issues. They're actually issues of, like, when it actually becomes material, it's going to be, the work will have to change. And I don't think that's going to be something as simple as saying, okay, if the material changes from something digital to something physical, it'll just be able to negotiate that. I think it's actually, there's a certain resistance in material and material systems and fabrication systems, which I think is going to make the work, hopefully, I think, better. It's not something which will, like, I'm not concerned about the work becoming watered down in some way when it gets built. I'm actually interested in embracing all the kind of resistance that exists within those systems. I guess that's what I was trying to show in that very first project by saying, yeah, it's probably feasible to mill all the formwork for the tower, but it's a lot more feasible if we wire cut it all. That's going to change the geometry, but I think that there's actually something in that new geometry which is perhaps more interesting than there was in the other. So I guess that's an example of where it might start to change.
I'm gonna try and pick up one of your toss questions, if you don't mind. Is that I found it really interesting when you were talking about the symmetry that I actually didn't catch until you pointed it out. The strange close symmetry, which I guess is a part of judgment that I probably unfairly introduced this as beauty, but that's pretty close to this strangeness that you're talking about, that it requires a closeness to be, it requires a closeness and not a purity. If this was purely and geometrically symmetric, we would see it as something else. And this is, I think, the point that I'm very curious about that comes back around to the synthesis, is that you are responding to contingencies in your work with the fireplace columns. Occasionally there are these contingencies, and we've seen this semester kind of juicy morsels of horrific projects that try to synthesize pure geometries with the contingency that architecture has. And you can only imagine how bad this is. Like pure forms, fireplace, horrific. Whereas in your project, well, they can't. It's impossible. So I guess it's the messiness that's allowing for a synthesis. And what I'm curious about is how much of that are you, like when you get to these contingencies, how much of that are you explicitly modeling and then fuzzing in to kind of mask a synthesis? Does this make sense? And maybe the answer is in your feedback loop.
Well, redundancy is a really useful tool in, or useful condition in this work. So, I mean, there's always a lot of whatever it is that we've got, and that's operating in different ways at different times. So, it's very different to have, like a bundle of fibers is going to operate it'll operate structurally, it'll operate in terms of surface, it'll operate in terms of texture and ornament. It won't do any of those things optimally. But it's conceptually possible that as a whole will be more optimal than putting an optimal structure with an optimal surface with an optimal something else. But I'm not trying to make an argument about optimization. Just that there is a lot of depth within redundancy which can be used in various ways. That's one way of dealing with it. Another way of answering that question is, I guess it depends on which project. Because some projects are more, they really do go from a range of scales from something which is highly modeled to something which is given a lot of freedom. So like the house in Malibu is something which there's not a lot of stuff emerging in there outside of the pattern. But in other projects, I would say that the whole thing emerges. But it's partly that some of those things can be resolved. I guess the argument I'm making is through redundancy. But to go back to something you brought up, and both you have brought up, which is about how judgments are made. And this is something that Brandon and I were discussing briefly over lunch, and it's really hard to describe. Like, I've tried to write about it before, and I've never been able to write about it very successfully in terms of why we make a decision about something. But that communication happens with people in our office. So with the staff in our office or interns, I spend a lot of time sitting down with people talking about why one curve is somehow better than another curve, or a set of, or the way a couple of curves relate to each other, or something about when a surface is, at what point does a surface become too relaxed, or, what is the right amount of, at what point is order readable? And those communications are actually made through like strange little diagrams or sketches or lots of hand movements, and trying to, it's a sensibility ultimately. It's a highly subjective sensibility that it's hard to articulate and only is kind of like communicated through lots of examples and hand waving, I guess. I don't know if that's not a very intellectual answer to your question, but it's the way, I guess that's the way it happens.
Should we just end on the best question of the night? Is that a good? Roland, thank you very much.
Thank you.